Welcome back to our architectural design sessions. I'm Derek, this is Cale. This session we are going to do some architectural designs around off-chain storage, how they relate or contrast with oracles and cryptlets, and then we're also going to talk about some scalability considerations with regard to your blockchain. So let's start in real succinctly, if you don't mind. What is the difference between an oracle, a cryptlet, and off-chain storage, because they are all off the chain? So what is the difference between them? Maybe draw out how they are architecturally different.
Sure. Yeah, so let's talk through offline storage first. Maybe what we can do is basically define what all these are, and then you'll see the differences between those two.
Let's do that.
Yeah, so if we talked about, let's just label it here, offline storage.
Offline, off-chain.
Oh yeah,
not on the chain.
Yeah, let's go ahead and make it off-chain, because it might not necessarily be offline.
Right. So offline storage, okay.
So off-chain storage, basically what we're talking about here is the model that we talked about before. So when we're talking about storing things up here, whether it's Bitcoin or Ethereum, we definitely have to be cognizant of how much data we're storing in there. We can basically break up the data contracts and have a bunch of little data contracts holding data. That's one model that we could use. But there's still severe limitations around that.
Right.
And the blockchain's not really built to kind of serve as that function. It's really about the ledger function at its core. Being able to prove that something originated from somewhere.
It happened, it exists, you moved it, that kind of stuff. Don't put your cat pictures in there.
Right.
Okay.
So basically we have this big ledger here that we've been talking about, and this is our transaction log, for lack of a better sense. So this is our trans log, just like a database, and that's what we're keeping track up there on the blockchain. Now, as we start bringing data in, like, okay, here's our smart contract, right? We got this guy on the blockchain. He basically, instead of storing all the state in here, which we totally could do, you can start storing state. Eventually, you're going to hit a limit to what you can store in there.
Because it'll just get slow. It'll be too hard to upgrade because it's expensive. Okay, yep.
So the thing is, we can basically just bring, and I'm just going to use the database symbol here, but this could be NoSQL, this could be file systems, this could be Azure File Store, it could be blob storage, it could be any of that stuff. So just consider this a repo out here that we can store stuff in. And essentially, whenever we're writing into our smart contract, instead of just writing into here, we can basically write our transaction into our data store and then calculate the hash off of it, right? So now we have a hash.
Okay.
Whatever. So we have a hash over here that we can use, and then we can basically sign this with our key, so we know who the owner was of this, and then we can basically have that as part of our state in our contract.
So this would ultimately build up, as you were querying back your state, this would ultimately build up that tree of being able to prove that this data exists on your blockchain, but the actual blob or the binary bits of it are sitting down in your database, so you're proving that that data has both been signed and has not been altered and that kind of stuff.
Yeah, correct. And the thing to think about there is the verification is what you're looking for there. So when we have this digital signature that we have referenced in our smart contract and also in our transactions history, everything that's built up, we can actually prove when things changed and to that extent, all those kind of things. But the actual data itself is abstract to us. We don't really care what it is.
Okay, so now explain to me how that relates to either an oracle or a cryptlet.
Sure. And in the cryptlet sense and in the oracle sense, both of those mechanisms are there to provide us two things: off-chain compute and off-chain storage.
Okay.
The problems, we kind of talked through the pros and cons of oracles versus cryptlets earlier, so I won't rehash that.
This is the 1.0. This is the 2.0.
Yeah, you can think of it in that sense. But essentially, we can build oracles on top of cryptlets, so it's kind of a superset, when we think about it from that sense. But what we want to do here with these oracles versus cryptlets is to be able to say, like, I don't want to have like crazy compute over here. One reason, IP protection.
Because this is all public. Everything in here is in bytecode and can be reversed.
Yep.
Okay, so essentially, if I understand what you're saying here, is an oracle or a cryptlet is providing like compute power sitting up in the cloud that we talked about how they're attested or they're verified. So I could have off-chain storage holding all my data. I've got an Oracle or a Cryptlet providing extra compute power. Both of those help to reduce the amount of gas as well as the overhead and increase efficiency, possibly increase security, because this is in bytecode, which can be easily reverse engineered, and stuff sitting up here would not be exposed to the general public.
Yep. And another model that flows with this is basically, so when you say that it's more secure, we still have to trust our Oracle, right? So we had some issues around that, but Cryptlets is attempting to solve some of that to some extent, to be able to say we can run that securely up there. But being able to offload that also gives you the better transactions per second, which is a big thing with blockchain. We haven't talked a whole lot about scalability, but transactions per second, because it's asynchronous and because we have to wait for this block time, it actually is kind of an issue right now compared to some of the systems we're used to. Sub-second, transaction times.
Right. So over in Bitcoin right now, there are times when it's 20, 30 minutes before a block gets confirmed. In Ethereum, it can get that big on the public network. On the private network, it's a little bit different, but it could be as painful as that if you have a B2B scenario where you have multiple members in the consortium spread out all over the world. Just speed of light gets in your way. So that actually dovetails really nicely into the scalability conversation. So
one thing before we touch on that is I wanted to talk about Cryptlets. One other feature that we're looking at there with oracles. Remember, we're coming in, so we're coming from the outside into the blockchain. We can call in. One of the features that we're trying to do with Cryptlets is basically be able to annotate these things. So in .NET, when I'll just use .NET for an instance, but Java does the exact same thing. If we have a function definition, and then we can provide in brackets above that these attributes, right? About something.
You're decorating it.
Correct. So we can use these annotations to actually index into a Cryptlet. So we can say, hey, when you execute this function, the variables that you're going to use, actually, I want you to go get them out of this thing.
Okay.
When you go to execute this function, here's the code I want you to execute first. You can delegate actual calls over to this Cryptlet and have him go do some compute for you and give you a result, or just give you some state back.
So that really provides a way of separation of concerns. I mean, you're putting the compute elsewhere, you're putting the storage elsewhere, and you're using the blockchain for what it's really good at, triple entry accounting.
And anchoring, right? Anchoring.
That's right. You're going to attest that that data is valid or that compute is valid.
Correct.
Okay, great.
Cool.
Scale?
Yeah, from a scaling perspective.
Scale, Kale.
Yeah. So one of the things we talked earlier about was scale. Adding more nodes to the network doesn't obviously make this thing go any faster, because
it actually makes it slower.
Because they actually have to coordinate and resolve this issue. But one of the things I wanted to touch upon was like an enterprise. So this is what we're kind of focused on with these private blockchains, especially the enterprise market. What kind of unique challenges are we seeing right now from looking at the mining that's happening out there right now, even if we spin these templates up we have right now? So one of the things you got to be aware of when you start setting these things up is, so we could spin up, and I'll say this is consortium member 1, and this is consortium member 2. We'll just say there's 2 up here right now.
So these are 2 businesses, 2 different networks?
Correct.
Okay.
So maybe this guy's running on-prem. And this guy's running in Azure, right?
Of course he is.
So basically, this guy says, I want to spin up a bunch of nodes, mining nodes, and let's say there's 3 of them. And this guy says, I want to spin up 3 nodes. So now there's 50% here and 50% here, right? So no matter what happens, as Derek was mentioning, when the confirmations actually happen for the transactions, neither one of these guys can take over the system.
And that's simply because they're sharing the same amount of compute, they've got the same amount of voting power.
Correct.
Okay.
Even if this guy spins up, bigger machines, and this guy has slower machines,
right?
There's still 50% here. He may get the blocks, he may get the incentive, but we don't care that much about incentive in enterprise.
Not an enterprise one, right? So these could be huge VMs, and these could be little bitty ones.
Right.
Okay.
But still, they got to have 50% from each. They have to have 51% in order to have it.
Okay.
Right. So if we had this model and then we say, okay, well, what happens if this guy loses a node, right? So what happens if this guy goes away, and now he's down to 2? Well, now the percentage has dropped, right? I don't know the calculation there, but this guy's going to be less than 50%. This guy's going to be greater than. And I did them backwards.
You did them backwards, yeah.
Sorry about that. So this guy's going to be greater than, and this guy's going to be less than.
We're very excited about our Surface Hub. There we go.
So essentially, it's lopsided now.
Uh-huh.
If this guy wanted to kind of
He could
subvert
be
the
bad.
system, yeah, he could be bad and take over the system. It's just something to kind of think about as you start laying these networks out. And mining's kind of hard to do in the enterprise right now because it doesn't fit the same model. Now, proof of stake and some of those algorithms that are coming out, and there's other algorithms that companies are developing to change the consensus algorithm so we don't have to have the mining aspect.
Yeah, because essentially in an enterprise environment, this is a very computationally unfruitful exercise. You're basically having these VMs run at 100% CPU for 24 hours a day, so you've got a higher carbon footprint, you've got a higher infrastructure cost, you've got whatever the case may be. If it's I/O bound, that can be really expensive. So changing it over to a different type of mining algorithm in the enterprise space, like proof of stake and some of the other ones, could be very beneficial to an organization so that they don't have to have such esoteric mathematical calculations going on behind the scenes.
And we've been talking about proof of stake for a while, but just from a super high level, to just give you a sense for what that means, instead of having to compete through this mining operation to this
Who finds
game,
the hash fastest?
we basically, in that model,
first.
you have to escrow money up front. So
Okay.
everybody is given a certain amount of virtual tokens, let's call it, and each company can use those tokens to say, I'll process that block.
Okay.
But obviously, there's a limited amount of those, so somebody can't just take over the whole network and say, I'll process every block.
Right, because when you create that Genesis block, you initially allocate X amount of, in this instance, Ether, and it goes to the initial. So in a proof of stake, just real briefly, in a proof of stake algorithm, you would assign X amount to one node, X amount to another node, and then they would have equilibrium.
Right, and then it gets more complex from there. You can imagine that once you use some of your Ether, you have to wait so long and those kind of things.
The gas and then yep, okay.
So that's just a kind of a super high level of like what we're talking about there to kind of help this mining operation so that we don't have to do mining as much. And these things are evolving. I mean, this is a very fast changing space. So we're going to see even more come out, I'm sure, in the future.
Yep. So hope you enjoyed this architectural drawing, and we'll talk to you soon.
Thanks.